It's a different chapter in the book, so just keep that in mind, but you have a worksheet assignment for today. This will be expanded on in the next section starting Monday, and then the next section. Okay, so we will be taking this a step further, but we're keeping it very basic today. So recognizing situations modeled by linear and exponential functions, and then graphing exponential functions. Okay. So an exponential function, the most basic form of that is either f of x or y equals. That's just function notation. A times b to the x power. Sometimes a is visible, sometimes it's not. So if it's not visible, that's just 1. But a will be a number other than 0. B will be a positive number of any type. And then x is the exponent. That is where you would input values if you were graphing. So some examples of exponential functions: 2 times 3 to the power of x, 4 to the power of x, and 1/2 to the power of x. So you'll get variations of that. Okay, so once we get into graphing, you'll see a couple of those. We're going to start off with comparing linears to exponentials. Okay, but your main focus is on exponential. Exponential is a version of a nonlinear function. There's a lot of different types of those. Okay, up until this point, except for absolute value graphs, we've largely dealt with just linear functions. So if we were to graph a linear function, which we will not be today, the rise over the run is very constant. It's increasing or decreasing by the same thing all the time. Okay, addition or subtraction, increasing. Exponential functions would start out flat on one side and spike on the other. Sometimes they drop from the other way, but they will be curved up one direction. Okay. So linear, the rate of change remains constant. On exponential ones, the rate of change increases by the same factor or ratio. Okay. So linear functions, rate of change is constant, and exponential functions, the rate of change increases by the same factor. So just what I mentioned there. So in these 4 tables, you're going to have to do some tables in your worksheet as well. You're going to identify both how the x values are increasing or decreasing, or however they're changing. So think about it as a pattern versus the y values as well. So on all 4 of these, how are the x values increasing? By what? 1. Okay. So you will have to mention that in your answers because we're determining if they're linear, representing linear functions, or exponential. Actually, this one just says determine whether or not it's exponential, so that would be a yes or a no. No would mean it's linear in this case. On all of these, the x values are increasing by 1, but in your worksheet, they might be increasing by 2, by 3, by 4. All right. Now, what's the pattern in the other column? This one. It's increasing by 3. Okay. Now, that is a constant rate of change. Okay. Meaning it's the same thing every time by adding and subtracting. So this would be a linear function, therefore it's not exponential. So you would say no if you wanted to write it's linear, that's fine. Now where it says explain, I'm going to give you a verbatim explanation. You can use the exact same wording on your homework when it asks you to do that. Okay, but you have to start by describing the x values. Now the x value verbiage is going to be the same every single time, regardless if it's linear or exponential. So you would say the x values, so make sure to write this down so you can duplicate it in your answer, have what's called a common difference. I'll explain that wording in a second. Of 1. And the y values have a common difference of 3. If you want to abbreviate difference to diff, that's fine. Okay. Now, the x values will always have a common difference. If it's adding 2 each time in the x values, you'll just change it from a 1 to a 2. Okay. If it's adding or subtracting, it is automatically going to be linear, or basically non-exponential at this point. So today it'll either be one or the other. With the y values, you can even write the f of x values, but it's the same thing. This word, difference, will change whether it is a linear function or an exponential function. So between the 2 explanations, that's the only thing besides the numbers that's going to change words. Everything else is going to be the same. So you can use the same wording the whole time. So the x values have a common difference of 1. The y values have a common difference of 3. Now let's say we were subtracting instead. You would change that to a -3. That's the only difference. Okay. So if both of them are adding or subtracting, linear. But it has to be the same number. It can't be like +2, +3, +4. That's a different type. Okay. So over on B, again, the x values, they're all the same. But keep in mind, the ones on your homework are not. But you'll have to list what they're doing anyway, because it's important. How are the y columns increasing?
+1/2.
So this would be +1/2. Is 1/2 to 1 +1/2?
Yeah.
Is 1 to 2 +1/2?
No.
No. Okay. Now, that's why you have to check all of them. So make sure just because the first two are +1/2, the other one is not. So that means it's not going to be linear, but you're going to have to tell me how it's changing. So instead of adding, what other operation do we use to increase numbers? Multiply. Now, starting with, how do you get from 1 to 2 by multiplying? Times 2. Okay. 1/2 times 2, is that 1? Yep. Okay. And 1/4 times 2, 2/4 make a half. So that would be exponential. Okay. Now it looks linear to start with, which is why you have to check all of them. Okay. So since it's multiplying instead of adding or subtracting, this is what an exponential one will look like. The x values will be the same no matter what. It's the y column that is what matters. So yes, this is exponential. Now the x value wording is the same, so you just repeat that. So the x values have a common difference of 1. Now the reason I'm using this wording because it comes up a lot, so I need you to get used to seeing it. X values have a common difference of 1, and the y values have not a common difference because it's not adding or subtracting. It's a common ratio of 2. Okay. So this word is what changes between linear versus exponential. And then obviously the numbers. You can use this exact wording on your homework. Okay, just change the numbers, obviously. Any question on that? I want you to try the next two. So C and D. You can use the exact same explanations depending on which type it is. Your showing work is the +1 +1 +1 or whatever the number is. Okay. The y value for the common ratio. So I'll scroll back. So if it's exponential, the y values have a common ratio instead of a common difference. That's just the only word that differs between the two. So what type is C? Exponential. Why? Obviously the x values are increasing. What are the y values doing?
The y values have a common ratio of 2.
Good. Y values have a common ratio of 2. Now, as soon as they start differing, so this would be a +1, so you could always approach these by process of elimination. So start with adding first. If they don't match, go switch to multiplying. Okay. So this would be +1, that's +2, +4. That right there is going to throw you off. So times 2 times 2 times 2 is how these are changing. Okay. Now, one thing that's going to come up in your homework, so you would list it because you need to write it out. It's just like B. Okay, so the x values have a common difference of 1. It's actually the exact same numbers and everything. So wording is exactly like B. Okay. What if this was divided by 2? It's still exponential, but how would you write the common ratio of what? Of 1/2. Okay. Because if I were to, let's say, do 4 times 1/2, what's half of 4? 2. If I did 4 divided by 2, is that the same thing? So if you're dividing by the number, the common ratio would be the reciprocal, but it's still multiplying. So if that comes up in your homework, if it's divided by 3, you would say there's a common ratio of 1/3. Okay, so just convert it into a fraction if that comes up, but still common ratio. What type is D? It's linear. So in this, the way it's worded, the answer would be no. If you wrote linear, that's fine with me. Okay. The y values, what's the common difference?
-2.
-2. Okay. So with the division, you would change it to ratio of a fraction. So whatever you're dividing by, put in the denominator. With the linear ones, if it's by a negative, so you're subtracting, just do common difference of -2 instead of positive. Because if you add a negative to something, it's the same thing as subtracting. All right. Questions before we move on to the back? So use the exact same wording on your homework. Okay. Is everybody clear on what the wording should be? All right. Let's zoom back out here. So we're going to just briefly discuss this. This will come up more so in word problems and different graphing types next week, but I wanted to at least introduce it to you. So functions of the forms. So notice that the forms are the same. A times b to the x power. A is going to be larger than 0, so positive number. B is greater than 1. Those are called exponential growth functions. If the b value, meaning the base of the exponent, is larger than 1, that is growth. Functions on the form a times b to the x power, where a is greater than 0, but b is between 0 and 1, so it's still a positive number, but it'll be a fraction or a decimal less than 1. That's called exponential decay, which we'll talk more about in a second. Anyone know how to pronounce that word? You want to try?
Asymptote.
Asymptote. Okay. We're not going to get into that a ton, asymptotes. We deal with all the time in Algebra 3-4. The Algebra 3-4 students are actually doing exponential functions. We're just taking it a step further with them. But we deal with asymptotes all the time. I'll show you in the graph where it would be, because it's an invisible line. Okay, but it's a line in which the graph approaches but never technically touches. So once we graph one, we'll show you where that is. It may come up in the book. I haven't looked that far ahead to where it might come up, where you have to identify where it is, but if you have a visual of the graph, you'll be able to identify where it's at. But there's no harm in learning what that word means. So I kind of summarized this. We're not going to get into domain and range and behavior yet, but the different graphs, this is what a growth graph would look like. It would start really, really low and then spike. So I mentioned this earlier this week when COVID started spreading. It was really, really flat, not a lot of cases, and then it made a huge jump. That would be growth, an example. The last section we did notes on Monday, we had the multiplication of insects. That would be growth. Does anyone know a real life model of decay? Where something starts very high and it drops by a lot and then drops by a little bit less, until it flattens out. Well, that's the shape of it, yeah. Okay. The price of a brand new car, as soon as you drive it off the lot of the dealership, it will drop like $15,000 in value. You try and bring it back the next day, they're not going to give you the full price back. That's how it works. Then the next year, it would decrease by a little bit more, or a little bit less, until it's about a few $1,000s when it's really, really old. Now, obviously, the cars at Barrett Jackson, this does not apply to them because they went back up. Okay. But in most cases, if you went to a Ford dealership and you got a brand new car, brand spanking new car with no miles on it, drove it off the lot, you bring it back the next day, you are not getting the same amount back because it depreciates. Okay, so that's an example of that. All right. Now what this looks like in the function, so we're going to be graphing these. Now I gave you your table. I want you to have 5 points. If you want to use the exact same x values every time. So I gave you tables on your worksheet, but they're completely blank. The x column is blank too. If you want to use these same 5, that's fine. But you can kind of do any of them, but it needs 5. I would do at least 1 to 2 negatives. Okay, so be aware of that also. Now, these are written in a times b to the x power. this would just be the b to the x power. The b value is 2 larger than 1. Yes, that would mean this would model a growth function. So this one, after we graph it, should look like the one right here, where it starts out flat and then spikes. Is this larger than 1?
No.
No, so this one is a decay model, so it will start high and drop. So it's a good way to check to make sure you graph points properly. Okay. So the reason I left space up here is I'm gonna show you the work that you need to do in order to figure out what goes in the y column. But since x is the exponent, you're plugging these in to where the exponent is, and then we will be simplifying. Okay. Now these numbers will be small enough you won't need a calculator, but in your homework, there's a good chance you might. So first off, -2. If I plug that where x is, how do we deal with negative exponents? Since you were just quizzed on this yesterday. Change it to a positive by moving it to the denominator. So that'd be 1 over 2 squared, and what's 2 squared? 4. So the y value for -2, is positive 1/4. Okay. Now the same thing with -1. What's to the negative first? What does that become? 1 over 2 to the first, which is just 1/2. Stop there. 2 to the 0 power. 1. Okay. Don't forget that rule. So this is where it's applied. Now the last two I would hope you could do in your head. What's 2 to the first power? 2. And 2 to the second power? 4. Now the way these are, do you guys notice this 2 and the 1/2 are reciprocals? And then 4 and the 1/4? That's not a coincidence. It's supposed to be that way. Okay. Now that's provided there's no other transformations, which that will be next week's expanding on this. So go ahead and graph them. Blot those points. So obviously 1/4 will be just above the x-axis. -1, 1/2 will be halfway. Now the reason we want 5 is if I did this 3, that looks like a straight line. It needs to curve. Okay, so these 5, now is where it starts curving. It starts getting nonlinear. Okay, and then it will gradually spike by more and more and more as it keeps going. Now can you do more than 5? Sure. But I'm asking you for 5. Okay. So does this model growth like it should? Starts low on the left and spikes on the right. Okay. That's because the b value of 2 is greater than 1. That's why that would occur. Now that word at the top, asymptote, I want to show you where this would be. Now the way these graphs work, the asymptote is the line that the graph will approach but never actually touch. So this end of the graph on the right side is going up forever and ever and ever. It's not going to stop. It's just going to keep getting steeper. This side of the graph is going to get closer and closer to 0, but the fractions will just get smaller and smaller and smaller and smaller and smaller. So the asymptote is the x-axis in this case. It will get closer and closer to it, but won't actually ever touch it. That's what an asymptote is. So it's a boundary of the graph that it limits where the graph can go. Okay. We may talk more about that next week. I haven't delved too far into the week yet. But that's what an asymptote is. It's just an invisible boundary of where the graph cannot go. Okay. So if that comes up, that's what that is. Question on that one? So since this one's decay, because 1/2 is less than 1, but it's still a positive, the graph should look like it's flipped around. It should start high and drop as it moves to the right. Now with negative exponents, so I gave you an extra negative in this case. Now, last year they told me that they don't think I mentioned this, with the negatives on the outside if there's a fraction inside. Now could you guys like to use the term distribute, even though I caution you with that word. So apply the outside exponent, so you have 1 to the -3rd, 2 to the -3rd, and then rearrange them. A shortcut to that, to kind of jump there, if you flip the fraction inside, that can change to a positive. So what's 1/2 flipped? 2. So that would become 2 to the 3rd power, which is what? 8. bless her, this is, I didn't mention that. I don't think it came up a bunch, but you could have used that. I think some of you figured it out, which is great. Okay, but either way, that's what you get there. So, how would we approach 1/2 to the negative second? What would that become?
2 to the second power.
Which is 4. 1/2 to the negative first.
2 to the first
To the first
power.
power. The last two we should be able to do in our heads. Anything to the 0 power? 1. The only time a 0 won't be 1 is if there's something else with the 1/2. Like out in front of it, it'll be like 4 times 1/2 to the 0 power. That's different. 1/2 to the first power would just be 1/2. Now I picked these two for a reason, meaning the two that we're graphing 2 and 1/2, they're reciprocals each other. So these are direct opposites. So the -2 1/4, +2 4, these are reversed here. So if we had done +2, it would be 1/4. I just gave you an extra negatives. Okay. So this one will start higher, -3/8 way up here. And then -2 4, it's dropping by a lot, and then a little bit less, and a little bit less, and a little bit less, and it will keep going, but it will never actually hit 0. Just fractions and decimals get a lot smaller. Okay. So that would be a decay function for that reason. Okay. So question on the graphing. You only have 2 in your homework. Do you think you can handle that? Now, there's one more part of your homework that I don't have an example on, although you should be able to figure it out. I think some of you may get a little confused, so I'm just going to make up one. So, on your homework, you're going to have 4 tables. We already did 4 tables, you're going to have 2 graphs. Then you will have 3 more of this type. It's going to say, you don't have to write it down if you don't want to. Evaluate, I'm just going to make up a function. 2 times 4 to the x power for x equals 2. What do you think it's asking you to do?
Substitute 2 for x.
You plug in 2 for x, you substitute that in, and then simplify. Just like we did up here, we were plugging those x values in and simplifying, you're doing the same thing. So this would be 2 times 4 to the second power. Now do you do exponents or multiply in order of operations? Exponents, so what's 4 squared? So this would turn into 2 times 16, which is 32. So it's asking you to plug that in for the exponent and simplify. Could I combine the 2 times 4 and then square it?
No.
No. Okay, we just did these. This has an exponent of 1 attached to it. Those are not the same base. So do not go combining those. Okay. So does everybody think they can handle that stuff? It's 9 questions. The last 3 are like this. Don't forget if that was a -2, drop the 4 down, and you do 2 over 4, so whatever power. Okay? So I'll pass